let's look at 9.4, reflection and symmetry. We all know what symmetrical means, right? Okay, so it's an object that has symmetry if it's balanced. I feel like this is the key to life these days. If you can find balance, you're a genius. Balance and can fit onto itself by reflection or rotation. These are all words we're going to be looking at and getting into. Reflection, you sort of already know what that means, right? We've actually done that with the x-axis and the y-axis. And rotation just means taking an object and rotating it, whether you rotate it 180 degrees or 90 degrees or 360 degrees, right? Familiar terms? Okay, take a look at these shapes. If we take a look at this shape, how many lines of symmetry are there? Or are there any? First of all, what is that? Batman. Are there any lines of symmetry? Is this symmetrical? Yes. How many lines of symmetry are there? 1. Does everybody agree with that? Where is that one line of symmetry? Going straight down the middle. Everybody good with that and get it? Pretty straightforward? Okay, does this thing, oh look how nice that is. Isn't that nice? Does that have a line of symmetry? No? Scientifically speaking, no. So if we really get into the details and specifics of it, even if we look at, can you see that from where you're sitting? Do you see that there's, although it almost looks symmetrical, do you see there's very subtle differences? Like the little dots that I've pointed to, and just even the colors. There's a little bit of difference, but it's almost symmetrical. Do you see that? If we were to generalize this, if I were to say we're not going to get into the nitpicky little details, where would you say a line of symmetry could go if we were going to generalize it and kind of roughly? Right down the middle. It's almost symmetrical on both sides if we were to do that. But if we look at, again, there's a lot of things in nature that are perfectly symmetrical, but it depends on how detailed we get. And that's probably true of most things, actually. Good? Then there's this. Isn't this nice? Are there any lines of symmetry? Look closely at it. Are there any lines of symmetry? If so, how many? 2? Does everybody agree with that? Where's the first one? What's the first one that stood out to you? Right down the middle. Oh gosh, that's crooked. Well, this is embarrassing. Like, oh, just pretend it's perfect. Good? Where else? Is there another one? Horizontally here? Does everyone agree with that? Do you see that in real life? There's a lot of situations where you would see symmetry naturally happening, symmetry and reflection. So do you see this one has symmetry and reflection? Okay. Equilateral triangle, does that have symmetry? And how many, if so? So I saw people pointing to this one. Yeah. Is there anywhere else where it would? This one? Anything else? Oh, I drew it crooked, but do you get the point? Ugh, it's looking pretty bad. Is that it? That's probably it. We get that? So basically, if you go to each corner, each end point, and draw a line through that, we'll get where the symmetry is. And this one, it's already drawn, but do we see all of the various lines of symmetry that exist on that one? So far, so good? Kind of review and not really new stuff. Then there's something called a tessellation. Have you heard of tessellations before? Did you do these in grade 8? No. Okay. Well, tessellations, this is one of the fun areas in math where we get to sort of combine math and art. It's the covering of an entire plane with congruent. Do you know what congruent means? What does congruent mean? Like maybe you've heard of congruent triangles or congruent angles. What does the word congruent mean? Want to take a shot at it, just based on the words I just used? Congruent means, yeah, identical or the same. Yeah, so the same copies of the same image with no holes or overlaps. So basically the pieces fit perfectly like a puzzle. So if we zoom in, do you see what's going on there? It's actually just a series of triangles that have been shifted, rotated, and fit together. But the use of color almost gives it this 3D-like effect. Can you see that and picture that? And believe it or not, that's math, because these shapes, putting triangles together and creating this artistic sort of display, involves a lot of math. And there's actually a lot of math using tessellation that occurs in nature as well. So there's one example. Here's another one. You can sort of see the image in the center. They've drawn in the eye to make it look like a face, the image in the center, but do you see the general shape around the outside? And the key part to this is that, kind of like a puzzle, each piece fits with the other. So together these form what we would call a tessellation. And of course you could color it in and you could do all the rest to make it look more artistic, but that's the idea behind it. Good? Here's another example of what it looks like. Again, if you were to look all the way through, it's harder to see it with the black ones, with this background especially, but basically, what does that look like to you? Lizards. It's like a series of lizards that have been rotated and turned around so that each part of the shape fits into the other, just like a puzzle, and together it creates what's called a tessellation. Reflection, we kind of talked about. Oh, you know that. You don't need that definition. But here's an example of a reflection that occurs naturally in nature. Isn't that beautiful? So, a reflection we looked at like when we were dealing with the triangles and the shapes. And here's an example in nature where you would see this happen, where if you have water that's completely still, it acts as a mirror and reflects back the image that's above. And do you remember learning about, what do we call this thing in math? Quadrants. So see how we have these 1, 2, 3, 4 quadrants. Together we call this whole thing the coordinate plane. Does that sound familiar? We did this like months ago, I guess. And if we were to reflect things from one quadrant to the other, here we'd have a positive x and y value, right? Because it's to the right and up above. But if we flip it and reflect this dot over the y-axis, we'd get a negative x value, but still a positive y value because it's up there. If I then reflect that down, my x is negative and so is my y. And if I took that and reflected it over the y-axis, now my x value would be positive, but the y is below the x-axis, so this y is going to be negative. So that's an example of where the reflection that we see in nature shows up in math on our coordinate plane. Good? Okay, so, have you ever played Tetris? You know about Tetris? Do you see that Tetris is basically, we could play Tetris for our class today. Do you see that Tetris is basically this idea put together? So it's based on reflection and rotation and all of these things we just talked about. And tessellations, because you're getting the pieces to fit together. So there's an example of what that would look like. And here's your assignment.